Okay, so let's continue to explore the space-time diagram. There are many things on the space-time diagram that we can get without having to directly look at the equations or the Lorentz transformations, which we'll get to, but many relationships we can figure out from the space-time diagram, the geometry on the space-time diagram. So space and time, let's put on the space-time diagram the space and time axes of the moving observer, right? So from our perspective, we measure space and time like this, and we can put on the space-time diagram the way that space and time are measured by an observer that's moving at some speed given by this angle. Right? The closer this line is to being diagonal, the closer the speed is to the speed of light. So it's a precise quantitative statement. Here's the x bar, and let's drag it down this way, drag this down that way. That looks pretty decent. And now let's get a sense of how to divide up space and time, so to speak. So from the perspective of the observer or experimenter that measures x and t to be perpendicular to each other, so there could be an event here which represents some position in time at a moment t equals 0. So something happens here at t equals 0. If something happens here, it's happening at the same time. It's still t equals 0, and so on, all along here and all along here. So at a later time, all of space at a given moment in time is given by horizontal lines, right? We go parallel to the space axis to get all of the events in space at a single moment in time, at a fixed moment in time. So here's a later moment in time. Here's all of space at a moment in time which is greater than t equals 0, and so on, right? So I'm dividing space and time up into slices of space at increasing moments of time t. Right, so these are slices of space x at greater moments in time t. Let's now think about, let's put some events on here, and then we'll look at this from the perspective of x bar, t bar. So let's say that we consider two events. Let's say event A and event B. Now these are clearly two events that, from the perspective of the observer that measures space and time to be x and t, A and B are happening at the same time, whatever this time parameter corresponds to, right? So we just trace this back to here. This also traces back to there. We move along the spatial axis to get the time. We'll see that that's not the case from the perspective of x bar, t bar. But let's first divide up space and time according to the moving observer that measures space and time according to x bar and t bar. So again, by the same strategy, we're going to move along horizontally to the spatial axis to get our slices of space at certain moments in time. So all of space at t bar equals 0, all of space x bar at t bar equals 0 is this red line here, because all the events here trace back to this time here. Here's the t bar axis, and that's t bar equals 0. So at a greater moment in time, t bar, all of space x bar looks like this. And so on. So let's divide up. This is space and time x bar t bar divided up into slices of simultaneity, right? So these lines represent all events that happen at the same time t bar, not at the same time t. Okay, so those are some of those, and if I can go below, although I didn't go below, but I should, for completeness, if this is t equals 0, that's also a t bar equals 0, because the origin is common, but I can make slices that go below that. These represent slices of space x at negative moments of time t, and the same thing for x bar t bar, something like that. And so on, and maybe stop before I make a mess of this. But notice that while events A and B are simultaneous according to one observer, the observer that measures space and time as x and t, event B, I have to trace it back along the spatial axis, which is this red line here, all the way to this time t bar. And if this is t bar equals 0, this is some negative time, whereas event A, which is closer to the origin according to, according to both observers, this event happens in time t bar equals this, which is greater than t bar equals 0. So event A, so t of A is later than or greater than event B from the perspective of the moving observer, whereas TA is equal to TB from the perspective of the observer that measures x and t. So strangely, in order to ensure that the speed of light is always the same on the space-time diagram, a 45-degree line, we find that simultaneity depends on the observer.